Good morning, and thanks, Josh, for the introduction. I am indeed Robert Hundt, and for those of you who don't know me, hopefully very few of you, I'm at Google for almost 19 years. I've done all kinds of compiler projects here. C++ compilers for x86 or ARM, an open source CUDA compiler, a high-level synthesis toolchain called XLS. I was the original software lead for TPU starting around 2013. So it's been quite a while. And what else can I tell you? I wrote a book on quantum computing, so I dabbled in that space. So I've tried to do it all, right? One thing is missing, though, and I will come to that a little later. So that's me. And for those of you who don't know what OpenXLA is, hopefully only a few of you, here's a brief overview. It's a compiler toolchain, right? No surprises there. Inputs are JAX, TensorFlow, PyTorch. It goes through the interface, high-level operations, StableHLO. There's an interface, PJRT, sort of like take this graph, compile it, and run it interface. There's a bunch of optimizations in there. They, of course, are, there's platform-independent ones, platform-dependent ones. There is means for distributed computing. We used to have SPMD, and then Google DeepMind, of course, did their own thing, and then they married and had this child called Shardy, which is a very convenient wrapper around, organizing their sharding across, the tensors. We have support for tooling, profiling tools, obviously, and also, increasingly important, support for a variety of kernel authoring languages. And then code generation supported on a multitude of platforms, which is kind of cool in regards to fungibility. And also you are invited to add your own backend to this thing. There's means to do that. There's quite a number of interested, contributing, or just listening in partners. It's a large list. Last time I spoke here, we tallied up the market capitalization of these groups. If you add up the market capitalization of the people in this room, it's a very big number. I don't know how big the number is, but it must be very big. So here's sort of the high-level outline of my brief notes today. There's 3 Ps: performance, portability, and PyTorch are the themes. Obviously, JAX and OpenXLA is sort of the focus of these whole 2 days. I trust many of you were here yesterday. Performance continues to be obviously the big value proposition of a compiler infrastructure. And we improve our interfaces, our portability to other frameworks and infrastructures. And we have even support for additional frontends at this point. And finally, I will give a few notes on how we think about PyTorch and what we're going to do with that. So I want to say, these slides came back late yesterday evening. So for some slides, you might find me quite befuddled, and I will just pretend I know what's on these slides, but I might have to interpret them to a degree. Obviously, performance is super important. And here are a couple of examples. You might notice, or I noticed, that I don't know on which platforms those numbers were derived, but they're good numbers, which tells you performance has improved significantly. Here's a slide on CPU. CPU runtime has improved significantly. Historically, CPU was sort of the forgotten stepchild because we were assuming, early days that, machine learning will run on accelerators, GPU or TPU or whatever. And CPU we only built up, for correctness or debugging, those kind of things. But recently, it became more important, right? There is capacity crunch left and right. People want to run certain things on CPU. And we do host offloading, right? And I think our very first host offloading model, the CPU performance was too slow by the modest factor of 10,000x, right? So we knew we had to do something in that space, and I think things have improved significantly. Compile time, I think they succeeded in making it parallel. So this is where the 50x comes from. So goodness all about. CPU is no longer not important. It is important. We have staffed the team around it, so it's part of the story. Shardy, as I mentioned, very important. Everything these days is distributed. Nothing runs on a single device anymore. And, they are very proud of their MLIR-based way of expressing and modeling, and they have a shell where you can play around. And SPND alone is no longer cutting it. MPND is sort of the new big thing, and they managed, or they're working on bringing MPND to the Shardy infrastructure, which is also super cool, super convenient. You can play around with various distribution techniques. It should be open source. What does it say? End of Q3, so very soon. And you're, of course, always invited to collaborate with these folks and make sure your needs are being heard. I think this is super cool. There's an example, and I actually don't know what 1F, 1B pipelining means, but it looks good and colorful, so I'm happy with that slide. StableHLO, our sort of like versioned interface. The sort of working interface to the compiler is HLO, high-level operation or high-level optimization, however you want to call it. And we allow ourselves to change it at all times. It changes every day, every week. But this is not a good situation for anybody who wants to target the interface. And this is why we put sort of a stable layer on top of that, StableHLO. And StableHLO is evolving. The current most important developments are that they want to support symbolic shapes, right? Traditionally or historically, in our space, we were exclusively operating on known static shapes. And the reasoning here is if you want to distribute something over like 100,000 cores, you should know, how the sizes and shapes of these things look like, right? But this is not the case in other environments like mobile, right? And mobile brought to you this requirement that it needs symbolic shapes. And so we had the choice. We can either fork StableHLO and make sort of a mobile version out of it, or we can try to unify it, even though these symbolic shapes might not yet be fully supported for a variety of backends. And so we decided to do just that. So StableHLO sort of becomes its own entity, its own interface, and it has features that may not be supported by all backends. That's sort of a major shift in philosophy, if you want. There's some cleanup works. We had a different dialect in there called MHLO. I mean, as the MLIR ecosystem built up, people were just going crazy about dialects, right? There were like these cascades of dialects, whether they made sense or not. And some, didn't really make sense. So we have to clean some of those things up. And I think that's all I want to say here. So it's really cool work. It's fully developed in open source today. And so take a look. Here's a recent or interesting development. I mean, obviously, CUDA and NVIDIA GPU is important in any type of scientific computing. And so if you look at those, or many of those HPC workloads, you will find that they're mostly based on convolutions, right? And they can be executed very well on TPU, by simple CUDA kernels. And so I don't know where my researcher Billy sits today, but he came up with, I don't know where he is. He came up with this there. So if something is not understandable on this slide, we can ask Billy. So what he did, which I think is super smart, he takes these CUDA kernels, and there's some restrictions on the index expressions, I believe, but mostly he takes those CUDA kernels, wraps them into parallel loops, and once they're in loop form, he can raise them to HLO, and once it's in HLO or stable HLO, you can go through the regular compiler workflow, and you can run it on thousands of machines if you want to. There is even a paper and an animation. And what they did here is they take a climate model called Oceanigans, and it has about 200-ish CUDA kernels. They succeeded in raising them all, right? And then they wrote the paper. I think it's a submission to the Gordon Bell Award at supercomputing. And yeah, it works. It's a collaboration between many entities, universities, and supercomputing groups. So it seems to work. It's actually quite exciting. And a lot more people in the HPC community are taking a closer look. Oceanigans is actually written in Julia. And so what Billy also did, he invented or he built this binding to XLA, or And with that binding, obviously, it can run on TPU, GPU, CPU, right? There have been some Julia bindings in the past, but they were incomplete. And my impression was, well, that project's kind of dead. But with the Reactant interface here, the results are amazing. I mean, you see the curves down there. And again, I don't know what they mean, but they seem really impressive. And so I believe the performance results are really good, right? I assume the baseline is the dotted line, and so factors better, which should be no surprise if you're able to parallelize, right? And I think we will share the slides, and there's a collab. You can click on that and play around. It's quite impressive. So, I mean, in summary, right, for these last couple of slides, think about it. There's a whole range of CUDA workloads we can raise into XLA and run. Julia is now supported pretty well. This slide tells you what is supported. I actually don't know what's not supported. I guess we will find out, or you will find out as you try this out. But I think it's a large subset of Julia that's being covered at this point. Finally, a last couple of notes on PyTorch. I mean, as you know, we have a PyTorch XLA binding that goes through lazy tensor. And in talking to Meta, you know, they don't really like that. And they ask us to get rid of it. As a matter of fact, Meta asked us to do a couple of things. They want us to have a really good eager mode that's fast and that's reasonably fast. They want the compilation to go through the Dynamo framework, a graph capture framework, and they want us to hook into Inductor as a compiler. And so we are working on a fast eager mode right now that requires almost no code changes, right? All you should have to do is change the CUDA to TPU or whatever your target is, and it should just work. Obviously, it's eager, and so it might not work super fast, but the idea really is that you can sort of overlap the compilation of ops or small graphs with the execution of those graphs. So the compile time constraints, which can be significant, because if you do tracing, right, your graphs become colossal. So in this sort of eager mode, it's very convenient. You have no compile time overhead. And performance should be within a number. And I don't know what that number is, right? Some people say, well, it's going to be 10x. I personally believe maybe within 2x. And we'll see. My gut feeling is it's going to be within 2 to 3x. So we have to see. But it's really, really cool. I mean, you don't have to change your code. And as long as your data layout and other parameters like fit on your device, you don't have to do anything. It will just work, which is kind of cool. Right, and we also believe that with relative, modest effort, all major PyTorch idioms for parallelization should work as well. We don't know yet how the performance should look like, but if they just work, at least you can run stuff and analyze it and see where the performance problems are, and then we take it from there. So I mean, what I said with the overlap of compilation execution of these ops or short graphs, if you really think it to the limit, we should really think about building, that's what I'm thinking about, like a full-on JIT, right? If you think Java JIT with recompilation and specialization and hyper-optimization, feedback-directed optimization, maybe some auto-tuning, if we would be able to build that, then, I mean, it would literally solve all problems known to mankind in this space, right? So, I mean, I'm excited about this prospect. It's just early ideas, but of course you're all invited to share and contribute in this space. I probably should have built a different logo there. In case you don't know, that original XLA logo that came out of one of those contests, logo contests, and then we liked it, and then the JAX people was like, hey, that's cool, we do the same thing. And I think we should probably do the same for the JIT if it becomes a real thing. Here's a slide on how we try to become actually more professional in how we develop and deliver software, right? Right now, whatever we pump out there is sort of the compiler of the day. And this is, works maybe so far, but will not work into the future. So we are, working on a more disciplined, a more structured approach of getting the software out there in form of, let's say, an SDK that has versioned releases. We may bind certain features to certain versions, right, to make transitions easier. For example, there's some super old GPU backend support for some old generations of hardware that nobody uses anymore. If you want to deprecate those, you can now bind them to a version. And if somebody needs to use it, they can use that old version. But basically, we have basic basic compiler feature stuff. As a matter of fact, I would almost argue that XLA is the only compiler in the world that doesn't have a versioning scheme, which, maybe is something to be proud of or not, right? There's thoughts about how do we make this compatible and all that, all kind of details. And I want to say this is one of the surprise slides, so I don't know what's in there, but yeah, so we will become professional. SDKs and version releases are probably the main features we are working on here. Just as last time, what is my wish list for this year? I want to open source all of the TPU-HLO, right? I mean, we've been working on the TPU compiler for 10 years. The architecture is a tiled architecture, as many of your architectures are. And there's a lot of good stuff in there that I think we should really push into the open source to allow people, to learn or to make even TPU run better or whatever. But it's super interesting and really cool stuff, and then we have to push it out. The current optimizations that live in the HLO space, many of those could just be seamlessly moved up into the StableHLO space, based on MLIR, as people these days kind of like it to be. This would mean that more of the software stack would be immediately available to more platforms. So that's something we want to do. These Python-based frontends, they do tracing, and you get like these colossal graphs, right? Everything is inlined, everything is unrolled. And you can work around this, with source changes and all that, but it's of course super inconvenient. And we would like to find ways to not do the full tracing, because that would dramatically reduce compile time, memory consumption, memory footprint on device, and those kind of things. And the last two, I mean, you heard me talk about this last time I was here. The compiler has a lot of flags, The number of performance-sensitive flags is a little smaller, but it's still too many. And in my opinion, in this space, it has been developed super fast. Time to market is always priority number one. And the developers of individual performance optimization passes, they're like, hey, it works on my particular problem, and I don't care about the rest, so let me put this under a flag. And so given this way, we have a lot of flags and compiler passes that are not developed really well. They only work in certain, circumstances. And that bothers me, and I think we should really reduce the impact those flags have, because what we fundamentally do with the flags, we put the complexity onto the user, right? The user has to learn what these flags mean in order to get good performance. And that's just not nice, right? And too complex. And then how you triage or support is just a mess. We have to really reduce the number of flags and the impact of those flags. And proliferation of kernels. That's really something that worries me. So, all these kernels, Triton kernels, CUDA kernels, you just name it. We have our own Mosaic TPU, Mosaic GPU, right? They are fantastic engineering solutions. In my opinion, they are the equivalent of assembly, right? You can hyper-optimize your code for any given workload, but it's great for performance if you want performance today, but it doesn't scale. It doesn't scale, and I'm a compiler guy, right? And so I believe these kind of problems must be solved by the compiler. And now we have this dilemma that kernels, they are faster in time to feature, right? Time to performance, they're just faster. You can do the same thing what kernels do in the compiler, but compilers is more complicated, more customers and all that, so it takes longer. And so the question is, how do we bridge that? It's an ongoing struggle, and somehow we have to, manage to contain the numbers of kernels in the wild. I can tell you, for example, within Google, there's an important model, and you will find over 100,000 different configurations running in the wild. And the hardest configuration is like 2 or 3%, and it changes every week. So if you hyper-optimize for any configuration, you're old news tomorrow, right? And so things move fast, in my opinion, too fast to really bet heavily on those kernels. At the same time, they are important. Performance is important. And as you know, the market seems to shift toward inference, and whoever can deliver the inference the fastest, the cheapest, has a good chance of winning. So now we have this dilemma, right? It's an ongoing struggle, but I think we will have to live with kernels, but we shouldn't have too many kernels. And how we get there, I actually don't know. But that's my wish list. My wish list is maybe we find a way to contain this proliferation. And I think that's pretty much all I have to say. Thank you very much. And I think we have maybe time for a question or two. So, I mean, SDK, I would think, is mostly a versioned packaging of all the constituents you need to run things, right? We should have proper versioned PyTorch, TensorFlow, JAX version, bridge versions, runtime versions, compiler versions, and all that for the various platforms. Such that, I mean, I'm super old school. The way I think about it is you give users a CD. What's on that CD, right? They should just put it in and they can run stuff, right? That's what we have to deliver. Today, I think it's different. Today, we tell the user in TPU land, here's your cloud. Now go out and find stuff, and maybe you get lucky and figure out how to run things, right? And that's what I don't think we should do. We should be more professional. I think generally, yes, of course. But I think what's required is that we open source, and potentially it depends on your target platform, right? That we may have to open up more of the HLO. So it depends on where in the sort of pipeline you are. If there's specific requirements, let's talk. We can make it happen. I mean, if you do your stuff in MLIR and you bind in HLO, you have a problem, right? Because you would have to lower back and forth between HLO and MLIR. This is one of the reasons we want to push things into the StableHLO world, because that's where MLIR lives, right? Or they live in MLIR there. So it depends where in the pipeline you would put that particular pass, right? I mean, we did think about this lowering back and forth to stable HLO and StableHLO, MLIR passes with all these dialects in the past. And there were some efforts, but they mostly failed, right? The back and forth, there's always something missing. So I think it's the best solution, the best outcome would be if you really push the things you need into StableHLO, and then you can hook yourself in there. Is there a timeline? I don't know. Do we have a timeline? We will have a timeline. Let's put it that way. I don't think we have one right now. So the question is, will there be documentation for the TPU compiler flags? And the answer is yes. It's actually an ongoing effort. Very soon. Very soon. Yeah, the question is if you have a really complicated CUDA kernel, right? All kind of memory and pipelining and this and that, right? And so my impression, and Billy might correct me if I'm wrong, the HPC people, and I hope there's not too many here, are mostly interested in running stuff at all. Not like super high performance, right? And so this is why the kernels we got in Oceanigans don't have that kind of super specific, pipelining and whatnot. But I mean, talk to Billy after, and maybe there's more to the story that I don't know. So it's pretty powerful. I'm not exactly sure about the exact limitations, and I think we have to materialize the exact limitations of what it can do, what it theoretically can do. There's probably a bunch of papers in there. I think Billy's writing one, and generally, so there will be limitations. I don't know where exactly they are. So the Dynamo to StableHLO is definitely in the plan. We work on this today, right? Today, the lazy TensorFlow is to HLO. Tomorrow, we go to Dynamo to StableHLO. And yes, we're negotiating, we're talking to Meta, what it would mean for us to get in tree. And I think we have a path there. I don't want to make promises, but that's obviously the right outcome. Okay. Well, thank you again. Thanks.